Let's look at significant figures. And with these, we're trying to estimate how precise we know an answer or a number. And so there are a few rules that we've developed to determine whether a number is significant. First, any non-zero number is significant. Second, any captured zeros are significant. Now, what do I mean by a captured zero? For example, in the number 1001, there are two zeros in the middle of the number. It's surrounded by non-zero digits. Therefore, they are significant. So this would have 4 significant figures, because there are 4 digits here that are either non-zero or the zeros are in the middle of significant digits. Place holding zeros are not significant. What is a place holding zero? Well, there's 2 different ways that a zero could hold a place. Here are 2 place holding zeros at the end of 1500. Those zeros are there to hold the place of the 1 and the 5, and they may or may not be significant. And we have to assume that they are not significant unless we're told otherwise. So this number assumes only 2 significant figures. Another example of this would be 0.012 or 0.012. These 2 zeros that are in front are placeholders. So they are not significant, but the 1 and 2 are. And so this also has 2 significant figures. Now, if there is a zero after a decimal point and a number, those are significant. Let's go back to our 0.012 example. If I were to add an additional 0, so it would now become 0.0120, now this has 3 significant figures. And another way to think about that is this last 0 does not hold the place of anything. Without it, the value of the number does not change. Therefore, it must be significant because we put it there on purpose and not because we needed to. The 0 in front of the 1, 2 must be there so that the value is the same value. This 0 does not need to be there in order for the value to remain 0.012. So this has 3 significant figures. Sometimes people will write a number with a decimal place, which is a little bit sloppy, to indicate that all of these digits here are significant. And this is a way to indicate that 1,500 has 4 significant figures instead of just 2. But that's less ideal. A more ideal way of indicating significant figures is to use scientific notation. Scientific notation allows us to be a lot more flexible with how many significant figures we're displaying, and it also allows us to be very precise because we simply only write significant figures down. If a number is not significant, then we generally do not include it in our scientific notation. As an example, we can go back to our 1500 and we could write that several ways. We can write it 1.5 times 10 to the third. And this indicates 2 significant figures, but we could indicate 3. Or 4, simply by increasing the number of zeros that we're writing in our scientific notation. And this allows us to actually specify 2, 3, or 4 significant figures, whereas before we were limited to only saying 2 or maybe 4 in kind of our sloppy way of increasing or indicating using a decimal here. Alright, so you've probably seen those, but let's also expand on significant figures inside of calculations. And there's a few rules that we need to look at here. So first, let's look at addition and subtraction. But I have an addition example prepared. So if we add 135.27 to 34.261 to 1.773, and we simply put those numbers in our calculator and add them up, we will get 171.304. Now the rule for addition and subtraction is that we go to the last decimal place, and that is how many significant figures actually matter. So if I look at this number right here, this actually has 5 significant figures in it. 135.27, that's 5 non-zero numbers, no question. That's 5 sig figs. And 34.261 also has 5 significant figures. But 1.773 only has 4. However, the first number only has 2 decimal places, so the significance ends right here. And that is going to limit us because the other numbers have 3 decimal places after the decimal. And so they are not limiting the significant figures. So this first number is the one that's limiting. And when we write our answer, we'll have to round it off to this second or hundredths decimal place. And so we would write 171.30 as our answer. All right, you've probably seen that. However, what happens if we have numbers that are expressed in scientific notation? Well, it's a little harder to determine what is the same decimal place because they may have different exponents. So if I were to add 1.70 times 10 to the 6th plus 3.201 times 10 to the 7th plus 8.04 times 10 to the 5th, then I have an interesting problem because not all of these have the same exponent, so I cannot say that this 7 is in the same position as that 2 because, well, it's not. And so the easiest way to deal with this is to rewrite all of these numbers using the same exponent. And this works with large exponents like 5, 6, and 7. It also works with negative exponents. You just have to think about it in a different way and be careful. So let's rewrite all of these with the same exponent, 10 to the 5th. If I can do this correctly. So for this 10 to the 6th one, I'll have to move the decimal place over 1 so that now I have 17 times 10 to the 5th. That should be the same as 1.7 times 10 to the 6th. And then with my 3.2 times 10 to the 7th, that is going to be 320.1 times 10 to the 5th. And then this one's already in the desired exponent. So I don't have to do anything with that. And let's add these up. And so I would get 345.14, 10 to the 5th. And using this, I can determine that I get one additional digit after the decimal, assuming that all of these are written as with the same exponent. And so I should round it off to this place right here, the first decimal point. And then while I'm doing that, I can also rewrite this number using appropriate scientific notation. So I'm back at 3.451 times 10 to the 7th. So that might be a trick that you might not have seen before. Now, for multiplication or division, we use the fewest number of significant digits, and we round our answer off to that. And so I just have an example for that. So if I take 23.1 times 14.2 times 0.051 and I put that in my calculator, I will get 16.72902. And a lot of times people like to write down all the digits because they feel like that's the best way of doing things. We don't want to lose information somehow. But this would be improper because this has so many significant digits in it. 1, 2, 3, 4, 5, 6, 7 significant digits, where the lowest number of significant figures came right here at 2. So really, our answer should only have 2 significant figures in it. And the others have 3, that's more than 2, so those aren't limiting us. So we should write 17. However, a lot of times that does feel like it's unnecessarily rounded, and usually we like to keep a little bit of the extra information, especially with low numbers of significant figures. If this number already had 4 or 5 sig figs, then we're probably okay with that. But when we round it off to just 2, it does lose quite a bit of information. So sometimes we'll write it this way. We'll include a digit that's not significant, but then some people will draw a line over the last significant figure to indicate really there's 2 significant figures here, but I was getting 16.7 as the calculation, which is a different number than 17, and that might be important even if there's additional error in this last digit. It should still be closer than the complete rounded off number. So, this is a little bit about significant figures, and thank you for watching, and we'll see you in the next video.